You can review content from Crash Course Organic Chemistry with the Crash Course app, available now for Android and iOS devices.
Hi, I'm Deboki Chakravarty, and welcome to Crash Course Organic Chemistry. In April 1986, an accident occurred at the now infamous Chernobyl power plant in the north of the Ukrainian SSR. The explosion of one of its nuclear reactors threw out a lot of the radioactive isotope iodine-131, which contaminated the nearby area, including anyone living or working there. In humans, this radioactive iodine affects the hormones produced by the thyroid gland. Thyroxine, for example, helps regulate the body's metabolic rate, digestion, muscle control, and brain development. Iodine is incorporated into thyroid hormones in an electrophilic aromatic substitution, or EAS reaction. The thyroid cells use any iodine they come across, radioactive or not. But the radioactive form destroys cells in the thyroid gland, and long-term, this leads to thyroid cancers. There are some medicines that doctors could prescribe after the Chernobyl disaster, like iodine pills, which contain potassium iodide, with non-radioactive iodine-127. If taken quickly after exposure, the iodine from these pills can temporarily satisfy the thyroid's need and prevent the incorporation of the harmful isotope. If a chemist wanted to make thyroid hormones in the lab, they'd need to think really carefully about the reaction. The iodine atoms are added right next to the OH groups on the ring, and EAS reactions have specific regioselectivity when you add multiple groups. So let's learn how this regioselectivity works. In episode 37, we looked at what happens when we add a group to a benzene ring through electrophilic aromatic substitution. But we only looked at adding one group. When you add another group through EAS, things get interesting. We count around the ring from the first group we added, kind of like a clock, except a clock with only 6 hours on it. For example, let's say we have 2 bromines on a benzene ring. If they're right next to each other, we have 1,2-dibromobenzene, which is commonly called ortho-dibromobenzene. If the second bromine is in the 3 position, that's called meta-dibromobenzene, and on the 4, it's para-dibromobenzene. After that, there's not really a 5 and 6 position. Because benzene has a plane of symmetry, we're just making the meta an ortho compound again. So there are basically 3 possible parking spots for the second compound. Now, to figure out which of these molecules we make in a reaction, we have to use our old friend, inductive effects. In episode 14, for example, we explored how alkyl groups are electron donating. They push electrons toward another group. This is why tertiary carbocations are more stable than primary ones. The inductive effect stabilizes the positive charge on the carbon. With benzene rings, chemists sort groups into electron-donating groups and electron-withdrawing groups. And since that's a lot to write out, you'll usually see EDG and EWG. Electron-donating groups, as the name suggests, push electrons away from themselves. Electron-withdrawing groups draw electrons towards themselves. The first group on a benzene ring is like a parking lot attendant, directing the following groups to one of 3 other parking spots around the ring. Electron-donating groups activate the ring, making it react faster than a plain, unsubstituted benzene would. They push electrons into the ring, making it more nucleophilic and therefore more likely to react with electrophiles in EAS reactions. Also, electron-donating groups direct the incoming group to park at the ortho and para positions. Electron-withdrawing groups, on the other hand, deactivate the ring, making it less susceptible to reaction than plain benzene. They pull electrons from the ring, making it less nucleophilic and less likely to react with electrophiles, which makes reactions slower. Also, electron-withdrawing groups tell the incoming group to park at the meta position. To tell whether something is an EDG or EWG, we don't just look at the electronegativity of the atom directly attached to the ring. We need to think about resonance structures. Let's take a look at an example, the nitrile or cyano group C triple bond N. This compound is neutral charge-wise, so any resonance structure we draw will have to be neutral overall, with charges that cancel each other out. We can draw a resonance structure where a pair of electrons from the triple bond goes to the more electronegative nitrogen, putting a negative charge on that and leaving a positive charged carbon. To figure out other resonance structures, we can use a strategy from episode 10. Basically, we find groups of 3 atoms that share electrons in p orbitals. So there has to be a pi bond and an adjacent p orbital with 0, 1, or 2 electrons in it. In this case, we have an aromatic ring, so that's our pi bond. And because we pushed electrons onto the nitrile group's nitrogen, there's an empty p orbital on the carbon. So we can mark these 3 atoms, number them, and swap around the electrons between carbons 1 and 3. The electrons in the pi bond move to the carbon of the nitrile, giving us a positive charge on the ring carbon. The formal charges help us keep track of these resonance structures, but overall, the charges still cancel each other out, and our molecule is neutral. Now, we can continue around the ring and mark other groups of 3 atoms that fit our pattern, moving electrons from carbon 1s to carbon 3s and forming more resonance structures. Eventually, we're back to the original structure with no formal charges. If we draw out our resonance hybrid, our parking lot situation is a little clearer. With partial positive charges, there's reduced electron density on the ortho and para positions. No electron-seeking electrophile is going to want that. The meta position has the highest electron density across the resonance hybrid. It's the best parking spot here. Plenty of room, no shopping cart blocking it, in the shade, you get the idea. So it looks like a nitrile is an electron withdrawing group. We'd expect it to deactivate the ring and direct an electrophile to the meta position. In a paper published in 1959, the chemists George Hammond and Catherine Douglas did this reaction and found this to be true. The nitration of benzonitrile gives around 80% meta-nitrobenzonitrile. Now that we've worked with an EWG, let's meet an EDG, phenol. It's well known that phenol activates the ring. We know that benzene doesn't react with bromine without a catalyst, but phenol does react spontaneously. In fact, it's so ready to react, the reaction keeps going until we make tribromophenol, or TBP. TBP smells antiseptic and has several uses, including as a fungicide, wood preservative, and for making flame-retardant materials. As we can see in the structure of TBP, phenol directs electrophiles to the ortho and para parking spots. And like the nitrile group, resonance structures can tell us why. We can use the same strategy and push one of the lone pairs on the oxygen into the ring, leaving us with a negative charge at the ortho position, but overall neutrality. By marking groups of 3 atoms and pushing electrons, we can move the negative charge to the para position, back up again, and we're back to where we started. Now we've got our resonance hybrid, and any electrophile is going to really like the look of those extra attractive partial negative charges and head straight for the ortho and para positions. The meta position isn't very interesting at all. It's like a tiny spot next to the dumpsters. Okay, so far we've seen a strongly deactivating electron withdrawing group, that was the nitrile, and a strongly activating electron-donating group, the phenol. As parking lot attendants, our deactivating group directed meta and our activating group directed to the ortho and para spots. What if we put an alkyl group on a benzene? Another thing we saw in episode 14 was that alkyl groups can donate electron density by hyperconjugation, which means the CH bonds can stabilize charge on adjacent atoms. It's a little more challenging to see where to push electrons this time. If we start near the alkyl group, we can make a secondary carbocation, or a more stable tertiary carbocation. Let's go with that and push electrons around the ring to figure out our resonance structures. From the resonance hybrid, we can see the ortho and para positions have more electron density, which makes them good parking spots for electrophiles. Alkyl groups are only weakly activating, since they don't have the extra electrons like phenol, so this isn't like the mansion of parking spots. And in practice, we often see more of the para product because of steric hindrance, especially if the alkyl group is bulky. Now, halogens with lone pairs are tricky. They're not bonded to anything else, and they're electronegative, so they're pulling electrons away. That deactivates the ring. That being said, we have to draw the resonance structures to see what kind of parking lot attendant they truly are. When we do, we end up with negative charges at the ortho and para positions, so electrophiles reluctantly get directed to those spots. There's another way to look at these tricky problems. We can imagine our electrophile parking at each of the 3 positions and then draw resonance structures. Here, we're looking for differences in stability, where the more stable structure means a more likely product. For example, here we can draw 3 resonance structures from the meta attack, while we can draw 4 from both the ortho and para attacks. The electrons on the halogen give these carbocations additional stability. We can even see that the intermediate made from ortho and para attack have a whole extra resonance form. Overall, the halogens deactivate the ring due to inductive effects, but direct groups to the ortho and para positions anyway because of resonance. If all of these curved arrows are making your head spin, there's a little tool that our consultant, Professor KP, taught us at her channel Molecular Memory for EWGs and EDGs. First off, if the group or substituent bonded to the ring has a formal positive charge, we have an electron withdrawing group and a meta-director. Positive charges pull electrons, period. Now for the tool. If the atom directly bonded to the ring is connected to an atom less electronegative than itself, the substituent is electron donating, activating, and ortho-para directing. On the other hand, if the atom directly bonded to the ring is connected to an atom more electronegative than itself, the substituent is electron withdrawing, deactivating, and meta-directing. This pattern will get you through most groups on aromatic rings that you meet. There are two pesky exceptions: halogens, which aren't bonded to another atom, and one more that we'll put on screen. But in this episode, we talked about how the first group on a benzene ring affects how incoming groups join the ring, electron donating groups are usually activating and ortho-para directing, electron withdrawing groups are usually deactivating and meta-directing, and we can draw resonance structures that show us which positions will be favored. Next time, we'll talk even more about EAS reactions and add benzylic reactions to our toolbox. Until then, thanks for watching this episode of Crash Course Organic Chemistry. If you want to help keep all Crash Course free for everybody forever, you can join our community on Patreon.